Assalamualaikum warahmatullahi wabarakatuh, and today I'm going to present about the electromagnetic wave in waveguide. First of all, what is waveguide? It is a structure that confines and directs the propagation of electromagnetic waves. Think of it like an optical fiber, but instead of transmitting light, it transmits electromagnetic wave. These waveguides are typically hollow metallic structures, and to understand why we use metal, we have to look at the boundary conditions. For a perfect conductor, the electric field inside is zero, so the tangential component at the surface must also be zero. Let's set medium 2 as the conductor and medium 1 as the hollow space inside the waveguide. Since there's no electric field in the conductor, its tangential component is zero. By using the Faraday's law, the tangential components must be equal, so the field in the hollow region is also zero at the surface. This forces the electric field to bounce back into the hollow region instead of entering the metal. And for TM waves, it needs two conductors, so they cannot propagate in that particular waveguide. Wa- Waveguide modes are the specific electromagnetic wave patterns needed for propagation through hollow pipes, fibers, or transmission lines. These modes are determined by the boundary conditions of the waveguide. Different modes have different field structures, and only certain patterns can actually travel from the guide. Now let's take a look at the TE10 mode, one of the most common modes in rectangular waveguides. In this mode, the electric field runs vertically from top to bottom in y direction. The electric field is maximum at the center of the waveguide with and zero at the side walls. For the magnetic field, it forms circular loops that encircle the electric fields. The subscript 10 describes the number of half wavelength variation across the waveguide. The general notation for this is TE subscript MN, where M and N indicate the mode numbers. For TE10, the 1 means that there is one half wave variation across the width of the waveguide. For TE20, the 2 means there are two half wave variations across the width. The first index refers to the width and the second to the height of the waveguide. What is cutoff frequency? Cutoff frequency is just the critical threshold that determines if a wave can propagate through a waveguide. For a rectangular waveguide, the cutoff frequency depends on the width, height, and mode indices. The formula is given by equation 1. So here, c is just the speed of light, and m and n indicate half wave variation of the field. Now let's apply this to the TE10 mode, which is the dominant mode in rectangular waveguide. For T-Eton mode, m equals to 1. Applying the formula, the cutoff frequency becomes C over 2A. This is called the dominant mode because it has the smallest cutoff frequency compared to all other modes. Notice that it is independent of the height B and only dependent on the width A. If the operating frequency drops below cutoff, the wave ceases to propagate and decays exponentially. Now let's talk about the phase velocity. Phase velocity is the speed at which the wave phase fronts propagate through the waveguide. Interestingly, phase velocity is always faster than the speed of light in the waveguide, and it is mathematically defined as v sub p equal omega over beta, where omega is angular frequency and beta is the phase constant. However, phase velocity doesn't carry any information, so it doesn't violate physics. Whereas the group velocity represents the speed at which the signal or energy travels through the waveguide. Mathematically, it is defined as the d as d omega over d beta, the derivative of angular frequency with respect to phase constant. Unlike phase velocity, group velocity is always less than the speed of light. This is the velocity that actually carries information through the waveguide. Since electromagnetic waves contain both electric and magnetic fields, the interaction creates a force that pushes the wave forward. This is called as Poynting vector, which describes the direction and magnitude of power flow. It is defined as the cross product of the electric field and magnetic field. To calculate the real power transmitted, we use the time average Poynting vector. This gives us the average power flowing through the waveguide over time. To calculate the total power transmitted, we integrate the time average Poynting vector over the cross-sectional area. This gives us the average power flowing through the waveguide. Now that we understand the power flow, let's move on to the impedance in waveguides. Before discussing the impedance in waveguides, let's briefly look at the impedance in the free space. In the perfect vacuum, impedance is a universal constant, approximately 377 ohms. Inside a waveguide, impedance depends on the three factors: signal frequency, cutoff frequency, and the intrinsic impedance of the material inside. It also depends on the operating mode of the waveguide. These factors make waveguide impedance more complex than free space impedance. So what happens when operating frequency approaches cutoff frequency for both modes? For TM mode, as f approaches cutoff frequency, the denominator approaches zero, so impedance goes to infinity. For TM mode, as f approaches cutoff frequency, the term goes to zero, so impedance drops to zero. In both cases, the wave ceases to propagate and we get exponential decay of the fields. So why we do waveguides over transmission lines at the microwave frequency? At the high frequencies, transmission lines like this one experience significant radiation losses and skin effect. Waveguides, being hollow metallic structures, confine the fields completely, eliminating radiation losses. This makes waveguides much more efficient for high power, high frequency applications, such as radar.